The only time we got like yelled at for doing it wrong was like, we accidentally actually, I don't think it was that big of a deal. We had like on the floor, one of our like tape measures on the floor. Like, your tape measure on the floor and you're like, yes. She was like, should it be? And you're like, yes, not. Me either. That's why I don't understand why it'd be a big deal that one.
Okay. No, of course you. But I wonder where it's. Hi. Is it gonna be on the pencil spot? We can try. I think it's just I'm really tired, but like. Me too. No, me too. We all thought that. When you know me and Aiden were talking, like everyone else was like. It was so funny when he was like, Monica, like, what themes do you want for your wedding? Well. They just love us, you don't understand. I know you don't understand, like, you don't love us, like, they love us. That long. You guys were really excited. I thought you were expecting to drop us off at night.
I was with big garden boy.
We gotta go back to or for karaoke. I was literally going. Well, we were in. I know, but I'm saying. I don't know if we can doubt that.
But that was how he.
I was like, down to myself before I realized that. I'm being so real. Yes.
Do I try to go free it? No, I don't too. I'm gonna go free it.
Okay, guys.
Getting you evidence. I need to sit down with Robin, like, here's our evidence, what's.
It's like, if you want to, like discussions and then. I gotta put a.
I don't worry until next semester when we have you again.
Oh, yeah.
It's so real.
Yeah, but we do that.
Good afternoon, everybody. All your homeworks are back. One of the things that I'm starting to realize is that you guys work so effectively together at LA sessions that your grades are starting to converge to one kind of uniform mass. Which is fine. That just means things are going well. So that's one of the downsides of not having exams. So I think next semester I might pull a homework out and put a midterm in the middle. Just to kind of get things kind of separated because I'm starting to lose a little bit of assessment. Everyone's doing really well. Obviously there's a range of doing well. I mean, I love giving you guys A's, but is it really an A if 60% of the class gets an A? So I'm gonna work on that next semester a little bit. Not to say you guys are gonna get worse grades. I just would put a little more assessment in it. This is always a moving experiment for me. Keeps things interesting. And so I don't get bored and get into a rut about stuff. So, but I know otherwise it's good. I've been getting statistics from the CLR of all the classes at the school. Joy and Kayla see on average around 6 to 7 times more students than the average LA does in the CLR. So you guys are really keeping them busy. We are currently, Joy and Kayla are currently #1 and #3 in the department in CLR for most hours being used. So you guys are making us, one of the things the university is trying to cut back on is hiring TAs that don't do anything, which is actually becoming a problem. That's not happening in PCAP. So keeping our students busy. So thank you. Let's talk, continue on with kinetics. Keep on trudging. Some of this may be a little bit of review for you. But we need to think a little bit about reaction rate laws a little bit before we really get into the nitty gritty of what kinetics really is. And we have plenty of time to talk about that. How many lectures do we have left? We have one next, with 2, 3, 4, 5 lectures left, I think that's right. It's Monday the 9th is our last day, correct? I think so. There's 5 lectures left. We have plenty of time to talk about kinetics. So let's just remind ourselves where we were last time. And I spent a long time trying to derive a very simple expression that you guys have seen before, which is the Arrhenius equation. And let's just remind ourselves how we did that. And let's set up a little plot here. The idea is that we're plotting this so-called reaction coordinate, which is some set of motions, right? We're taking a complicated motion where a molecule is reacting with another one. They're moving around and they're forming a product, and we're basically taking all those little motions and putting it on a line and measuring energy as a function of those coordinates. So it's a very generic way to look at things. But the idea is that we have some products or some reactants at some energy. Right? We have, say, delta G of reactants. And this, of course, the units are delta G on the axis here. And as the reactants break, we have to, generally we have the energy increases because you generally have to break bonds. And there's going to be some, what we call a transition state. Transition state, which is not a minimum, but it is a maximum along this surface, kind of a little hump that we have to go over. And once you get past that, you're free to form reactants or products. Right, we can say, for instance, this is a very exothermic process. Let me change colors. Right, and that this energy is minus delta G of products. And of course, the reaction enthalpy or the reaction Gibbs free energy is this difference. And the system has to go through this hump here, right? And the most important thing is that if we were able to calculate exactly what this coordinate looks like, the product and the reactants are minima on the energy surface. You can think of this as the Gibbs energy as a function of the coordinates. This over here is also a minimum. Right, so these are minima of Gibbs energy. Right, so they're equilibriums or places where the system can equilibrate. And they have to pass through this region that has positive curvature. Right, this is an energetic maximum. Right, so the idea is that the transition state, which is delta G, is the relative energy of the transition state. Which is not a real minimum, right? This is not a real structure in the sense that it can equilibrate. Does not exist. Rather, it is a critical point, if you will. You got to be careful with that word. Maybe I shouldn't use a critical coordinate, if you will. That the system must pass through to react. Okay. So the system never ends up at this point. Molecules that start here, they have to go up in energy and pass over. will end up over here, right? This is the only two options, if you will, on the surface, is the products of the reactants. They're either going to be here or here. They will travel over the transition state. So they pass over it. So they have to at least increase their energy by this much to get over to the products, but they'll never stop here. Right, and I'm going to give you and so what we came up with was that the rate of this reaction, K sub R, the rate, is equal to this number A, e to the minus delta G X transition energy divided by RT. Right, this is the reaction rate. Right, this is what's called the prefactor. Right, this tells you something about the number of reaction chances per second. We'll look at some values of it today. And then this is the transition state energy. Okay, so the rate at which these products form depend on two values. One is how many chances do the reactants get to react. Right? That may depend on the number of collisions. We talked about the vibrations of a molecule. It may have something to do with the vibrational frequency of the molecule. There's lots of different ways we can interpret this. But the real important thing is that it depends on the value of this transition state energy. Okay. Ultimately, this number really makes a difference. For instance, when we thought about SN1 versus SN2, it's not too hard to show that the prefactor between SN1 and SN2 for a given reaction really aren't that much different, because the materials kind of experience those chances to react about the same. They're at the same concentrations, the same temperatures, the same environment. So the A's for SN1 and SN2 generally are kind of similar, but the delta G's vary very wildly. And so, for instance, for methyl bromide, which goes through SN2, not SN1, the delta G for SN2 is much lower than it is for the SN1 path. Right? So this is really the number that matters here, delta G of the transition state. Transition state is really the number that matters. So I'll call this like the number one parameter for kinetics.
And you said for SN1, it's greater than for 2?
Yes, yes, because, okay, so let's talk about that a little bit. Why can I make that claim? Why can I make the claim that for methyl bromide, CH3Br, that the activation energy of SN1 must be larger than it is for SN2?
SN1 has multiple, or like has a transition state.
Well, it does have a transition state. So does this, but the height of that transition state is higher. Remember what that, let's actually, if you don't mind, let me bring up the notes from last class. And let's just look at that mechanism one more time. All right, here's our two options. Right, in order for methyl bromide to react SN2, right, you just need to break that bromine bond and form an OH bond, and also pyrimidalize this carbon a little bit. You got to shift the hydrogens.
So
Okay.
is the SN1, are you saying that the greater for SN1 than SN2 is only true for this reaction or for every?
Yes, for this reaction in
Oh,
particular.
okay.
Yes, for this reaction in particular. And the reason why we said that is that, again, this costs some energy. But the claim is that for a primary alkyl halide, right, where you have a methyl with a substituent, that ionizing it, right, if you say the transition state for SN1, if you will, is ionizing the CH3 into CH3Br and the CH3 plus and Br minus. Right, you heterolytically cleave the bond first. This costs more energy. Right, so if this is our transition state for SN1, the amount of energy to get to this point is much higher than it is to do this. So for methyl bromide, this transition state is higher energy, therefore its rate is lower. And the difference between the transition state energies between these two is significant. So the rate difference is significant. So that means that when the system reacts, this forms very rapidly, and this is really, really slow. So if they're in competition, and the system's product favors, so it doesn't go backwards. Right? The moment a molecule gets over into the other side, the product side is stuck there. Right? Which one's going to win out? Well, this one's going to win out because both reactions have the same opportunities, right? The molecule is reacting has roughly the same amount of opportunities each second. A is about the same. But the chance of having enough energy to do this is much lower than it is for this. It's much more energetically favorable, SN2. So if a molecule gets a chance to react, it's more likely going to do this than this. It doesn't get another chance to react again. It forms and then products and move on. So almost always it's going to do this instead. And this is just ignored completely. Okay. So both of these transition states, so both of these pathways are perfectly allowed for methyl bromide. It can do either of these. It can travel either way along the surface as it wants. But the fact of the matter is that you're only going to observe the products that form from the pathway that is most efficient. Remember, chemistry is lazy. It wants to exert as little energy as possible. So naturally, it's going to prefer the pathway with a significantly lower transition state energy because it has more chances to successfully react. Now, when I move this, just as a note, I'll just write this at the bottom. But if the substrate instead is T-butyl, right? If you have this instead, this is SN1 dominant. And what that says is that the energy of its transition state, which is CH3, 3C plus, it's a little ugly. All right, trimethylcarbon plus bromine minus this transition state is much lower in energy than the transition state where these methyl groups need to move away and do the SN2 product where the bond breaks and bond forms. Right? And the reason why this is much less stable is, of course, because of steric strain. Sterics methyls, the CH3s impede. And here, this is stabilized because tertiary carbocations are stable. All right. So for a tertiary alkyl halide, like T-butyl alkyl halides, you have two effects that improve the SN1 chance, right, and lower its and increase its rate. One is that at the SN2 transition state energy is very high because it takes a lot of energy to move those methyl groups away to fit the OH in from back. And also the transition state energy or the intermediate energy for the carbocation and for the T-butyl situation is much lower in energy because this is easier to make. It's just easy, it's more stable. You don't have to put in much energy to break that bond catalytically to form cations. It ionizes much more readily. And so you have these two competing effects, and so therefore the SN2 barrier for the T-butyl case increases. So the activation energy for SN2 increases, so it slows down the kinetics. And then the transition state energy for SN1 goes and decreases in energy, which speeds it up. So in this case up here, you have the opposite, where SN2 is very low energy and SN1 is very high energy at the transition state. And here you have the opposite, and therefore you have opposite kinetics. Okay? And it's only dependent on the relative barriers of those transition states. These two structures, if you will, determine the energetics of these structures determine everything about those kinetics.
Thank you.
You're welcome. So let's go back to a little more analysis about this, because the next question we should ask ourselves is, well, so we have an issue here. which is our rate is ultimately dependent on this delta G activation, right? The energy of the activation energy. But here's the problem. We can't measure the activation energy directly because you can never make molecules in a transition state, right? They don't exist, right? So how can you measure the energy of something that doesn't equilibrate out, right? So we're trying to measure something transitory. Right? How do we measure the energy of a state that isn't a real state? It's a good question. All right, but this math tells us a little bit of something, right? There's two things that we can measure in this system. One, we can certainly measure the reaction rate, right? We can just set up a chromatography or a spectroscopy solution, something to measure the intensity or the abundance of our products as a function of time. There's lots of different ways to do this. You can do it colorimetrically. Lots of different ways. You measure a pH, for instance. There's lots of different ways to measure the abundance of the product concentration. All right, so if you can measure the product concentration as a function of time, you can get this value. We can obviously measure the temperature. That's easy enough. So we have an equation that's got two knowns and two unknowns. So we can use statistics now to figure out the values of delta G and A. So if we can measure how Kr depends on T, that'll tell us something about how K depends on delta G and A. All right, let's think about that a little bit. Right, so the important thing is that Kr and T are easy to observe. And if you think about it, the relationship of K, think about dKr dt, right? How does Kr change with respect to T? Well, let's just do the math really quickly. That's going to be minus delta G over R times A e to the minus delta G over RT. Right, if you notice, right, we have, right, this depends on the value of delta G. It values on the dependence on NA, and it also depends on your value of T as well. Right, so the way that the rate constant changes with temperature depends on the values of delta G over A, right? It kind of is like the product of the two by this calculation. And so if we can measure how this changes with respect to temperature, and we measure the temperature, right, this is our input, we can maybe get a sense of what the relationship is. The slope, if you will, of this curve is something to do with delta G and A. Okay, so if we can measure Kr as a function of T, maybe we can pull out these numbers statistically, delta G and A. And there's really a quite very straightforward way to do this. And this is kind of the most classic way to measure kinetics. Perhaps you've done this before. You just didn't realize it, right? But we can take a lot. Let me just go to the next page. All right, so we have Kr is equal to A e to the minus delta G transition divided by RT. Right, so let me take the log of both sides. Now, you guys should probably see something that maybe reminds you of problem set 2. We did hex now. I gave you this equation looks a lot like the relative abundance calculation for the conformers. Remember the conformers the abundance was proportional to E to the minus energy difference divided by RT. It's the same statistics. Took the log of both sides and you got a linear relationship. We should get the same here. Let's just remind ourselves how that works. We get the log of the rate constant is equal to the log of the argument. Right? We can split this out as the log of A plus the log of E to the minus delta G over RT. So this says the log of KR is equal to the log of A. Now we have the log of something to an exponent, so we can bring the exponent out. Times the log of E. And of course, the log of E is just 1 by definition. Therefore, we have that the log of the rate constant you observe is equal to minus delta G activation divided by R times 1 over T plus the log of A. All right, well, this should look very familiar to you, right? If we take this and call this Y, and this M, this X, and log of A to BB, we have Y equals MX plus B, a linear regression. All right, so this is our trick to measuring delta G. So we do it indirectly. We can modulate, we have a reaction that occurs. We can measure how fast the products form, right, through spectroscopy or whatever you want to do, pH. Especially if the SN2 reaction, you can do it with pH, with a pH meter, right, because it's taking OH and removing bromine, so your pH is going to lower as the reaction progresses in water. If you do it in water, that is, right? And so KR is going to change. You change temperature, the rate at which the products form will change. And that, the ratio of that, basically 1 over T versus log of KR, is proportional to the activation energy in the slope. So, and then our, right, and log of A tells you something about the asymptotic behavior, basically at T equals 0. So this tells you, right, so indirectly, if we can measure, if we can linearly regress KR versus T, 1 over T, we can measure these things directly or indirectly. Right, this is, again, what's called this is the more traditional form. This is what we call more traditionally the Arrhenius equation, which is what I called the other form, but it's the same thing. Right? Often you'll see the Arrhenius equation written like this, because this is how an experimental chemist would use it to do kinetics. Right? Measure your rates at the different temperatures, and then plot 1 over T versus the log of the rate that you observe, and you get some nice answers on the slope and the intercept about your kinetics. All right, so let's think a little bit about some of the limiting cases for this system. What happens depending on the value of the activation energy? Note that if your system is very hot, such that the temperature, the amount of thermal energy is much greater than delta G, right? This basically says that KR is equal to A. Right? So if A is temperature independent, reaction is temperature independent as well. Right? You just have so much energy into that. You have so much energy in that system that every time it reacts, it will. And so it's ultimately limited. The rate of reaction is ultimately limited by how many chances it gets. Right? This is basically saying you have a 100% probability that if two things come together, that they'll react to form the products. So let me just write that here. So this says reaction probability is effectively 100% at this temperature. All right, but again, that doesn't happen very often. So rather, we should think about the relative values of delta G. Maybe that's more interesting because very rarely, this is rare. For reactions between two neutral molecules. Right, so if you take two molecules that are covalently bonded, don't have any unpaired electrons, aren't ionized, just normal molecules, this is very rare. Because generally you have to break a lot of bonds for molecules to react, neutral molecules. There's a lot of endothermicity in that process. You got to break those bonds before you can form new ones. So it takes a lot of energy. So typically this is not the case, but it is, especially in situations with radicals and ions. It can happen with radicals and ions. And we'll talk about that. I'll have some time to talk about radical and ion reactions before the end of the semester. What are some other interesting things? If delta G is large, this means that the delta G is large. Your slope here is very big. So small changes in T lead to large changes in rate constant. Right, so we often say that large activation energies, these reactions have strong temperature dependence. Right, something like we saw this, for instance, for the Haber-Bosch reaction, right? This has a really big delta G. We'll look up the delta G in just a second, actually, for that reaction. Or delta G, transition state energy, activation energy. So large activation energy means you have strong temp dependence. And again, we see that in some extent to Haber-Bosch, right? You really got to crank the temperature up for it to go. Combustion is another situation where that goes, right? Eventually you put so much energy and heat into your combustion mixture that it spontaneously ignites. That's what's called the auto ignition temperature. It tends to be pretty high for gasoline. But you can eventually crank the heat up that it becomes spontaneous. And again, the idea is that the rate becomes so quick that it happens almost instantaneously because it's got strong temperature dependence. Some reactions that have delta G is small, right? The other idea is you have a weak temperature dependence. We'll talk a little bit about reactions that have weak, small transition states. They're very interesting. And interestingly, that there are some reactions, so I'll try to find you an example of one before the end of the semester, where the activation energy is negative. And this has a negative temperature dependence. Which means it goes faster at lower T. Isn't that interesting? There are reactions that are cryogenically very, very fast that are very slow at 300 Kelvin. And that seems like an odd concept, but I'll explain to you what kind of reactions these are, and it probably on Wednesday, if not on Monday. But there are types of these reactions where, actually, so let me write delta G is less than 0 or greater than or equal to 0. So there are some that have zero activation energy. They're what we call barrierless reactions. Barriers to reactions tend to only work well at low temperatures. And I'll explain the theory of that when we get to it. But there are reactions that do have negative temperature dependence. Not surprisingly, in space, the most common reactions in space are the ones that have low activation barriers. One, they have fast rates, and also you're in space, you're cold. You can't have anything of a high activation energy because your molecules never have enough energy to get over it because they're damn cold. They're in space. So typically the only reactions that occur in space are ones that have low or negative delta G's because they're the only ones that are favorable. So that it's important what conditions we consider. Okay. What I want to do now is just a bit of math, really, really simple. And I want to take this concept and connect it back to equilibrium, right? I told you that there's some relationship between equilibrium and rates. So let me just show you what that is. It's a very simple argument. And this is why equilibrium will often tell you something about rates as well. If you're careful about it, there's lots of different ways you can actually measure rates based on looking at the equilibrium constant. I'll try to give you an example of that today. All right, so what I want to do now is I want to formally connect our equilibrium constant to our rate of reaction. Really, really simple math. Okay, so let's look at a system like this. So we'll just take reactant A. We'll form a transition state AB. We'll say this is A plus B. And then we form a product C. Okay, and so this is at delta G of A plus B. And this is at delta G of C. And we'll call this delta G of exclamation of the reactors, the activation energy, delta G double dagger. Okay, so let's think a little bit about the rates of this. Let me simplify this. Let me just call this A. Sorry, I'm sorry, yes. Let's go back and simplify this. B, B. All right, so we'll just have A to B. And we'll just call the transition state, looks kind of like A going into B. Maybe I'll do a little arrow here, slowly converting into B, some intermediate structure. Okay, so let's think about the rates here. All right, so the formation rate of A. All right, so we're going to think about the time derivative of A, the concentration of A with respect to time, right? So this is something we can measure, right? This is the rate of observed rate of formation. Right? The concentration of our, well, this is not the formation rate of A, but rather the depletion rate of A, right? Because it's removing A to form B. Okay. So this is going to be equal to, right? So we're going to think about how fast you're losing A. So obviously you're going to have a negative sign here because you're losing it. And it's going to, let's say, for instance, that the rate of reaction is Ka. Right, so that's the rate going this way. Right, so the reaction rate is Ka. Right, and it's going to be multiplied by the concentration of A. Right, remember these are all reaction rate laws. Right, these are rate laws from Gen Chem. Right, remember in a first order reaction where you go A to B, the rate of formation of the product of the depletion rate of the reactants is proportional to the rate constant times the concentration of the material. Right, if you have 2 times as many A's, then it will react twice as fast, right? All right, so let's think now about the reverse reaction. Right, because even though we're talking about A going to B, there's also a chance that B can go to A. Right, so call that KB. So Ka represents A to B, and KB represents B to A. Okay, so let's think again about the depletion rate of B. This says that the time derivative of the concentration of B is going to be equal to minus KB times the concentration of B. All right, really simple. Okay, so what we have now, let's think about in terms of A. All right, what's the total rate of let's say total rate of B or A, whichever way you want to think about it. We have a process which is going from here to here that depletes B or depletes A, right? We're losing A by forward reacting. But at the same time, it's competing with the reverse reaction, where B can go back over the barrier and form A. Right, so you have 2 processes that are occurring simultaneously. They're competing with each other. And of course, the rate at which they compete depends on the values of Ka and Kb. right? If one's much larger than the other, obviously that one's gonna dominate. Right, but every time we have a chance to lose A, we have a chance to lose B and form A again. And so there's this balance between the two. Therefore, the total rate of depletion of A is going to be equal to dA dt equals minus Ka times A, right? That's the rate of loss plus the rate of gain, which is the rate of which B forms A. This is B to A. And this right here is A to B. Right? So there's this balance between the two. Okay, so let's do a little bit of math. All right, so let's let at time equals 0. All right, so at initial time, the initial concentration of A is A naught. All right, we're starting with some A. And then let's assume that the initial conditions for B is 0. Right? So all A, no B. All right, so we can write dA dt as minus Ka times A plus Kb times the concentration of B at a given moment. Well, we can rewrite this now as minus Ka times A. But since A and B are the only things in the reaction, we can relate the moles of B to the moles of A from stoichiometry. So this is going to be Kb times A naught minus A. That should make sense, right? We can always write the amount of B as the leftover, the stuff that you don't have of A. That's going to be the difference between the current concentration at a given time and the initial concentration. All right, I'm just going to rearrange this expression a little bit. We have minus, what this says is we have minus Ka plus Kb times the concentration of A plus Kb times the initial concentration of A. Like this, right? I've just kind of rearranged that formula a little bit. And so this is equal to dA over dt. So we have this differential equation, right? This tells us what the slope, right? This is the slope of the time value of A, right? The concentration of A at a given time at some time t. Right? So we can calculate, right? We can calculate the time dependence of A by integrating this equation. So what we have now, we have the integral let me see how this math works. Sec. Let me break this down a little bit. So we have the integral of dA over minus Ka plus Kb A plus Kb A naught is equal to the integral from 0 to t of dt. And we're going to integrate this from 0 to t. Sorry, so this is from A naught to A of t. All right, so we're going to integrate this equation out. I'm not going to do the integral here. It's it's not that hard. Just a little bit of partial fractions. A of t is equal to kb plus ka e to the minus ka plus kb times t over ka plus kb. Times A naught. Okay, so what we get from this, again, just a lot of numbers. We have some constants in the numerator and the denominators, right? But we ultimately say that the the constant A is exponentially decreasing, and it decreases at some competitive rate between A and B as a function of time. So what we would expect to see, basically, is that this system looks somewhat like this if we were to plot as a function of time the concentration of A. We would start at A naught at T0, and this system exponentially decreases as a function of time. Right? So A of T, concentration of A of T kind of looks like e to the minus KAT. So the system decays like this. All right, so we have this big, let me move this equation over to the next page. We're almost done. We've done all the complicated math. That did not copy over, sorry. I don't know why this has a giant line through it. All right, well, I guess that's just going to stay there for now. Let me bring this over now. Okay. All right, remember now, so we want to connect this to equilibrium. So remember, equilibrium occurs at steady state, right, where we let t go to infinity. Right, the system is allowed to equilibrate forever, and eventually it reaches some equilibrium. Right, so now let's think about what A at t equals infinity looks like. Well, we obviously have Ka plus Kb here. The denominator, we have a Kb that doesn't go away. And then we have this term here, which looks like e to the minus t. Right, at large t, this becomes a very small number, so this goes to 0. So we're just left with Kb o plus 0. Times A naught, the initial concentrations, which is equal to Kb over Ka plus Kb A naught. All right. So this says that the concentration of A at equilibrium is equal to Kb over Ka plus Kb times the initial concentration. And what about BEQ? What's the equilibrium concentration of B? Well, remember, that's just the initial concentration of A minus the concentration of A at a given time, which is the equilibrium. Right, and this should give you, and this should be equal to Ka over Ka plus Kb A naught. And then what's our equilibrium constant? Remember, equilibrium now is the ratio of the equilibrium concentration of B divided by the equilibrium concentration of A. Right? Products over reactants.
I have a quick question.
Yeah, go ahead.
So this might be silly, but like B at equilibrium, like, is that just, that only works if it's a 1-to-1, right?
Yes. This math works no matter what, though. If it wasn't 1-to-1, it would still work out the same. You would still get the same result.
Why?
Well, okay, it would look different. It would look different. But the result I'm about to give you is going to be the same. Just give me a
I
second,
can live
okay?
with that.
What I'm trying to, yeah, just to give me a second. Well, we can look at that more carefully. We'll look at a situation that's more complicated than this eventually. As you can see, there's a lot of cancellations here. Right? It simplifies that KEQ is just the ratio of the forward rate divided by the reaction rate. Everything else goes away. So equilibrium in general, for any sort of reaction, we got to be careful about this, but for any one-step reaction, where you take some products A, some number of products A, and form some products B with rates K1 and K minus 1, reverse and forward, then the equilibrium constant is always equal to the forward divided by the effective rate, reaction forward rate divided by the reverse rate. So equilibrium measures the competition between forward reaction and reverse reaction. Right, this is how equilibrium and kinetics are connected. Right, think about it this way. Right, imagine KQ is really big, very product favored. Right, what does that mean? Well, that means that every chance the reaction gets to go forward or backwards, well, let's just think about it in terms of forwards. Right, K1 is large. That means the system has very, very high probability to go from the reactants to the products. Right, so you think of it as a function of time, A is constantly converting into B. And then every click of the metronome, or the unit of A, if you will, the prefactor, B, the products have a chance to backwards react to form A. Right? But maybe that's really slow because the system is very, very exothermic, right? So, right, let's just look at the diagram on the previous page. Sorry about this. Now let me just, oh my God, this is awful. Let's go back to this plot. Right, the activation energy here is some size. From reactants to activation energy, right? That's some size. But this reaction is exothermic. So the distance, the reverse reaction, which is going this way, has a larger activation barrier. Right, so let's assume that A to B has the same prefactor as B to A. Right, so the A's are the same. The only thing that changes the rates are the activation energies. So here, the activation energy from A to B is smaller than it is for B to A. So when A gets a chance to react, it will react to form B more readily than B will to react to form A. So allow that competition to run to infinity. A's are always getting a chance to make B's. B's very rarely get a chance to make A's. In the end, the B's, you're going to have more B's than A's. The A's are going to win out and form B, not the other way. So the equilibrium says that the system has more B than A, right? Because Ka is faster than Kb, right? And that means the equilibrium constant is greater than 1. Right? You have more products than reactants. And that's because delta G is less than 0, right? You lose delta G in this situation. Now think about it the other way. Imagine now this is here. Product energy is right here. It's endothermic. Delta G is positive. And the rate of A to form B is still the same. We haven't moved that at all. But the rate to form B to A, if the energy is right here now, is very, very fast because the activation energy is very small for B to A. Right? So this tiny little gap here. Sorry, for the people on Zoom, I know they can't see me do this. Right? If we instead drew our product minimum to be right here at this olive line that I'm dotting out, right? This is fast comparatively to this, which is slow, right? Because delta G is really small going in reverse, right? So what would happen here? Well, in this competition, A occasionally forms B, but every time B gets a chance, it forms A. It's got a very high probability of doing that. Let that time go to infinity, you're going to have more A than B. The equilibrium constant is less than 1, which correlates to a delta G that is positive. See how they all connect like that? This is really powerful because equilibrium only tells us something about things that are isolable, right? We can measure the isolable like isolatable. That's isolable is the right way to say that. All right, we have products and reactants. But kinetics may tell us something about other things, right? What if there maybe are minima in the middle here that the system transiently exists in until it goes off and reacts later, what we call intermediates. Equilibrium is not going to tell us anything about the intermediates, but the kinetics might. Kinetics are very sensitive to it, as we'll see. Right? So this connects again equilibrium and kinetics. Kinetics is kind of the true answer, right? In a sense, we get the full power. Equilibrium only tells us things at t equals infinity, and kinetics reproduces those results. And kinetics also reproduces the results all the way up to t equals infinity as well. We know everything about the reaction of kinetics. It's a harder problem. We have to know more about the product system, right? We need to know the activation energies, these prefactors. Right? We need to know more information, but we get much more power in understanding what's happening in the reaction with kinetics than we do with equilibrium. Equilibrium only tells us about the condition at one time point. Kinetics tells us the conditions at all time points along the process. Okay, what time is it? Good. Make it. I just want to get us set up for next class. So I just want to do a quick reminder of first order kinetics. Kind of just want to look at this very carefully. Right. Imagine that we have a reaction, very simple, where we take molecule A and we form P. This is kind of what we've been looking at, but let's just do the math very carefully. Right, we can always define a rate law. We typically either define it as the loss of our products or our reactants, or we can define it as the formation rate of our products. Right, and this is going to be equal to Kr times the concentration of A to the first power. All right, so let's talk a little bit about these rate laws really briefly. Okay, so general rate law. All right, imagine that we have a reaction that kind of looks like this. A plus B plus C plus dot, dot, dot goes to products P plus R plus S dot, dot, dot. Who knows how many products or reactants we have? We can always write, and let's add some stoichiometric coefficients to it. VA, VB, VC, VP, VR, VS. And so let's, for instance, write the rate for dA, dt. Right, well, there's going to be some rate. It's a negative because again, we're depleting. There's some effective rate that we measure. This is the effective rate, the observed rate. Rate constant. And we're going to multiply it by the concentrations of our starting materials to the power of some number. Right? And in general, NA, NB, and NC refer to the number of moles of these molecules involved in the transition state. Okay. So these values could be all sorts of things. So we often think that these numbers have something to do with the stoichiometric coefficients. Right. So for instance, if you have a reaction that takes two equivalents of one molecule and one equivalent of another, you would raise the concentration of the one that takes one equivalent to one and the one that takes two equivalents to two. Right, to the stoichiometric coefficients. This makes an assumption. Let me write this down. The assumption is that that would imply that two equivalents of that molecule are interacting in the transition state. So if Na, let's just say for instance in A plus 2B goes to C, right? If we observe experimentally that the rate of A goes as the observed rate constant times A times B squared, okay? This would imply that the transition state structure has two equivalents of B in it. Okay, but if the TS structure or transition state looks like this instead, where the slowest, the transition state step only has one version of one equivalent of B in it, and maybe the other one comes later in some step that doesn't have a barrier, then the rate you observe is not second order in B, but just first order in B. Okay, so these numbers, NA, NB, and NC, they may be the stoichiometric coefficients, but they might not be. Right? In general, they may not be. So I'll write that up here. Right, typically, Na, the order of the reaction is not equal to the stoichiometric coefficients, but they can be. It depends on the mechanism. Even more than it depends on the mechanism, it depends on the transition state. The geometry of it, whether it involves multiple molecules or not. Right? It could be even possible, it seems unlikely, but there could be a situation where A actually gets surrounded by many B's and therefore is extremely dependent on the B coefficient, B amount. Or for instance, it may be there, it doesn't matter whether you have 5 or 6 or 7 or 8 or 9 B's around A, and then there's very little dependence on B. B has a very small exponent in the rate law. Because it doesn't, B is basically just like a solvent. Imagine B was just a solvent. Right? It wouldn't really matter how many solvent molecules you have around it. So if you double the concentration of solvent, it wouldn't really change the rate at all. And so this number down here on the exponent on the rate law might not be a very large number. It might be a really small number because B might be a solvent. It doesn't really engage with the molecule that effectively. Yeah, go ahead.
So like, I mean, I get what you're saying, but I don't like fully understand like in a case how that would actually work. Cause like when you're describing that, it would be like B.
Yeah,
like just
so
around
you want to
B.
look, you want a counterexample?
Yeah, that'd
All
be
right, let me
great.
give you one. We'll analyze this next class, but let me give you a counterexample, right? So let me just give you an example of a reaction that I write down the stoichiometry for, and it's not the same as the rate law, right? That's what I'm asking here. We'll look at a bunch of examples of this, but let me just give you an example. We'll analyze how this works in a second, or not in a second, but maybe next class, or maybe next week, actually, now I think about it. Yeah, next week, next Monday, we'll analyze this. So here's an example. All right, take a molecule of H2. Let me make this a little bigger, sorry. Molecule Br2, and you make two equivalents of HBr in the gas phase. Okay. Right. So what would you naively say is the rate of formation or the rate of depletion of H2 with respect to time? What would you write here? Monica, what would you say?
I would say that it would be the concentration of H2. And then, yeah,
Times Br2, right?
Yeah.
Right, because there's one, so right, they're each involved 1-to-1.
shouldn't it be negative or just
Yeah,
negative?
sorry, thank you.
You're good.
Yeah, thank you. I'm just gonna put the negative out here, it doesn't matter. All right, that makes a lot of sense, right? Hey, the stoichiometry makes sense, there's 1-to-1. So let me show you what the real measured equilibrium or the real rate law for this is. I have it here somewhere. Where is it? 27, 28, should be on 29. I guess I didn't copy it over, sorry. Where did my problem go? There we go. Where are we? I've lost spot. We were working on another page, weren't we? Yeah, we were working here. All right. Sorry, let me find it here. Yes. Yeah. So let me rewrite. Yeah, that's fine. Okay. So the real answer to this, I don't have enough space for it. So let me move it over. This might tell you that it's wrong, that I don't have enough space for it in this little corner. So let me move this over here. Let me just add a new column, new page here. Right. So the real answer to this question, and we'll derive this in a couple of days, is that the time dependence of H2 with respect to temperature is equal to Kr times the concentration of bromine to the 3/2 power times the concentration of H2 divided by the concentration of Br2 plus another rate constant Kr prime times the steady state concentration of HBr. So as you can see, these are very different from each other. Even if we assume, right, let's assume that HBr is basically 0. You can see these are very different, right? So let's just do it. Let's do a limiting case where HBr, or rather, let's say where Kr is much smaller than Kr. Kr prime is much smaller than Kr. We can neglect this term here. And this would look like Kr Br2 to the 1/2 times H2. Right? So obviously it looks very different than what you would expect.
What's the difference between KR and KR prime?
There's two different rates in this reaction because it's a multi-step process. So here's the thing. So the great question, why do I have two KRs? Because there's two steps, there's multiple steps in this process that are competitive. This is a multi-step reaction. If this were one step, Monica would be exactly right. If you took a BR2, right, this is the picture that you might have of this transition state. Right, this is our naive example, right? What would the transition state look like for this process? It would look like this. It would form a square. Right, you're slowly breaking these and you're slowly forming these, right? This would have this TS consistent with naive rate law. But this is not the way it reacts. How much time do I got left? I got enough time already. Right? In fact, the mechanism for this reaction much more complicated. All right, we'll get the tools to analyze. It's not too hard to analyze. It looks scary, but it's not. This is a lot of math. The first step is what we call a radical initiation. This is a free radical reaction, free radical propagation reaction. This will be a radical initiation. That bromine radical that forms is allowed to react with H2 to form HBr plus hydrogen radical. We call this propagation. This H is allowed to react with the Br2 that's in the mixture to also form HBr and Br minus or Br radical. Sorry, no, that's wrong. Sorry, wrong math. This is a 3, 2. H can also react with HBr to form H2 plus Br. This is what we call termination. We're terminating the H. And then there's also a reaction that forms bromine, the reverse reaction. And this is also a termination step. Each one of these has a rate. And these rates are in competition with each other. Well, we'll do the analysis of this a little more carefully in a few classes. I just want to double check something really quickly. Move to the next page, 29. KR prime. So in this case here, what we find actually is that KR is a combination of multiple reactions. It turns out it's 2 times the rate of the second reaction times the square root of K1 over K5. And KR prime is the ratio of K4 over K3. Right? Very, very complicated. Each one of these steps actually are what we call fundamental or elementary steps. These reactions work exactly the way you would expect them to. I need to get rid of this too. But the idea is that the rate of this reaction is proportional to the rate of bromine atom times H2, right? So these are elementary steps. So K1 through K5 are elementary. I need to get rid of this. This makes it more complicated. Are elementary steps. satisfy that the stoichiometric coefficients are equal to the orders of the reaction. Right, so for instance, just as an example, for K2, the formation of hydrogen atoms in K2 is going to be K2 times the concentration of Br atoms times the concentration of H2, right? Just like the stoichiometry says. Right, so these are what are called elementary steps, which satisfy the simple expressions that you can read off the stoichiometry and know the rates. But the total mechanism for the reaction is actually a sum of all 5 of these steps, and they compete with each other. Right? The total rate of the reaction depends on the relative rate of this step with respect to the termination and the initiation. So if this terminates very, very rapidly, or the Br atoms disappear very, very quickly, they get consumed, the forward rate of the reaction is very slow because K5 is large. But if this reaction, if initiation is very effective, you can break Br very effectively, and you can propagate them in reactive H2, right? Say, for instance, your concentration of H2 is very high, so that every time you form one of these, this reaction occurs almost instantaneously. Your forward reaction is very quick, right? There's a competition. But remember that Kr prime is on the denominator. So this actually slows the reaction down. And it says that it's a K4 over K3. Right? So it says that if your termination, right, if your H atoms get depleted very, very quickly relative to the amount that they form, right? This is what H does. H reacts with Br2 to form HBr, right? It's one of the kind of key drivers of the products. So if this is very effective and this is very ineffective, Kr is very small, and therefore the reaction is very product favored. But if you're in a situation where their H's don't last for very long and they get consumed to form H2 in this termination step, Kr is very fast, therefore K4 is very fast, or Kr prime is very fast, and therefore your denominator is very large in your rate law, and this reaction doesn't occur very rapidly. Right, so the formation rate of H2 or the depletion rate of H2 or the formation rate of this reaction depends on multiple characteristics. You have multiple intermediates that are all interacting together, reacting with each other in a complex equilibrium, and the relative ratios of those concentrations will determine ultimately how fast the reaction goes, right? There are certain materials that drive the reaction forward, and there are certain materials that drive the reaction backwards. And we have to worry about the competition between the two. Right, and this is shown out and borne out in the kinetics, okay? This seems very complicated, but we'll have the tools to be able to analyze this problem. We'll derive this exact equation, I think, on Monday. All right, we'll be there. This is to give you some sense that things are more complicated than you think they are. Yeah, go ahead. Have a good one, guys.
So why would it be here for H, the radical? Because I thought if we're looking at Q2, it should be like the first. Then like maybe
Oh, I have a negative. It should be a negative sign.
Oh, okay.
Sorry, this is sorry, the DH. No, H forms from this reaction K2.
So then how come for like this one, we were saying it's like.
I don't
H2?
Oh, the negative sign's right here.
No, but I mean like it's this part being like H2 versus.
I can choose whichever one I want.
Doesn't matter.
It doesn't matter. Yeah, because this derivative is the same. If I put dBr/dt, it would be the same thing. Because H2 and Br2 are both being eliminated by the same rate.
Yeah, but I'm saying then how come here, this part's of the radical's a product?
Oh, I just picked that. I could easily just write it as the loss
That's
of,
why it's positive.
right, exactly. I just made that pick, but it's arbitrary, so it's either positive or negative, just depends on what I want to look
And
at.
also, when you have over dt, is that time?
Yeah.
Okay.
Yes, time.
I'm spending.
Your formation rate.
That's what I thought. I think you said temperature once,
Yeah, I meant.
but you said time all the other times,
Oh.
so.
Yes, ma'am, what's up?
So I'm still waiting
Yeah, we haven't changed anything yet.
Okay.
I'm still waiting to hear back from the dean.
Oh,
It's not my decision, unfortunately. It will get expanded. We're just waiting to see, what rooms are free. Because that depends on registration, just so you probably are aware.
Thank you.
You're welcome.
I guess, like,
The day that I have to pay for the spring semester.
Oh,
it's gonna be like,
I don't know what I can do about that, unfortunately.
yeah, I don't know.
You're one of 9 people in that situation, so.
Yeah, it's fine.
I'm sure the registrar knows. So if you have any issues that are really bad about that.
Yeah.
I think that as long as you're waitlisted, I think you're okay.
Okay.
If they start yelling at you, let me know, okay? You're welcome. How you doing, Matthew?